Okay, we were looking at tree structures to represent dictionaries, and in the last lecture we took a look at building a least cost binary search tree to represent a static dictionary. Today we're going to start our discussion of dynamic dictionaries. Okay. And for dynamic dictionaries we'll see a range of data structures, okay, each having its own pluses and minuses. All right, so to begin with, in a dynamic dictionary, the primary operations are you want to be able to perform a search, you want to be able to insert a new pair, you want to be able to remove a pair from your dictionary, and some additional operations that data structures for dynamic dictionaries support, at least tree-like data structures, are the ability to list the contents of your dictionary in ascending order of key, to perform a search by index, and to perform a remove by index. Okay. All right, so if you look at the complexities of the primary operations get, put, and remove, if you were to use a hash table data structure to represent the dictionary, your worst case would be order n, your expected, and really this is what you would see in practice almost all the time, would be order 1. Using a binary search tree, it would be order n in the worst case, and log n is the expected case. The unfortunate thing about this worst case is that the worst case corresponds to a case that is likely to happen in practice. So it's not like you could safely use this and say we're going to consistently get log n behavior. There will be, or there are real applications where you would get close to the order n. Okay. Unlike the hash table, where the worst case of order n tends to happen in an unrealistic situation. All right, so then there are balanced binary search trees where the worst case and the expected complexities are both log n. Okay. If you look at the additional operations I've listed there, okay, if you use a hash table and you want to list all of the entries in ascending order, here D is the number of buckets in the table. The only way to list the elements in ascending order would be to first go and find all of the elements in the table, and for that you'd spend at least d units of time going through all the buckets locating the elements. Having you found the elements in order of d or order of d plus n time, depending upon the data structure you're using, you would then have to sort them into ascending order, spending n log n time, n being the number of elements. Okay. So so for the ascend operation, that's what you'd spend. It's not just a worst case, but it's also the expected time to perform the ascend operation. If you want to do gets and removes by index, well then a simple approach to that would be to do what you did here, sort them and then pick up the ith one. Okay. A more involved approach which would bring the complexity down from, I guess, d plus n log n to d plus n, would be you collect all the elements and then you use a selection algorithm which in order n time can find the ith element from an unsorted collection. Okay. So instead of the n log n, you could do it in order of n. Okay. But there's really no way to get it down below the d plus n. Okay. If you're looking at indexed binary search trees, again, these are not balanced. We just throw the indexing operation onto it that we discussed a few lectures ago. Then you're spending order n to do the ascend. Okay, that's just an in-order traversal. Okay, and you're spending order of n also to do the get and the remove, because the height could be order of n. If you go into the balanced mode, then this remains order n, and that becomes log n. Okay. So for the secondary operations, a balanced binary search tree is going to give us very good performance compared even to a hash table as far as expected performance is concerned. Okay, so we really want to take a look at balanced binary tree structures. Okay. And all of these are really based on unbalanced binary trees. So what I'd like to do is just have a quick review of how the operations are performed on an unbalanced binary search tree so that we're all on the same page with respect to the background material. Okay, okay, so here is a binary search tree. If you want to insert an item, well, then you just search for that key, the key for that item, and wherever you fall off the tree, that's where you put it in. Okay. So if you want to insert a pair whose key is 35, you'd search for 35. It's bigger than 20, smaller than 40, bigger than 30. You fall off here. That's where you put it in. Okay. So you find out where to put it. You get a node and link it in. Okay. So that's an order of height complexity. Okay. If you want to do a remove, well, then the remove breaks down into three cases. You have a case where the pair you're removing is residing in a leaf. When it's residing in a node whose degree is 1, and then it's residing in a node whose degree is 2. Okay, so those are the only three possibilities for the remove, assuming the remove is successful. Okay, if the item is not there, well, then you don't have to do any work. You just say, I can't do the remove. Okay. All right, so if you're removing from a leaf, for example, you could be removing the 35, 25, 18, 7, 2. Okay. Right. Well, then you need to first find the leaf. Okay. So you're given the key, you perform a search, you end up over there. Once you find the leaf, you just change the pointer from the parent to null, and you got rid of the node. Okay. Right. So all you have to do there is change the pointer from the parent to null, and you're done. Okay. If you're removing from a node whose degree is 1, okay, for example, you're removing the 40, okay, or you're removing the 15, or you're removing the 8. Right, in this case, if you're removing, say, the 40, you simply change the pointer from the parent, assuming you have a parent. Okay. If you're the root, well, then you just disappear. Okay. But if you do have a parent, then you change the pointer from your parent to your single child. Okay. All right. So you change that pointer, and that cuts that one off, and essentially this node is no longer part of your tree. All right, here's another example. We're going to take out the 15. Okay. So you change the pointer from your parent to your single child. Okay. All right, the final case is you're removing from a node whose degree is 2. Okay. So for example, you could be removing the 20, or you could be removing the 10, you could be removing the 6, you could remove the 30. Okay. All right, so let's say we are asked to remove the 10. Okay. So to remove the 10, you can't really play the strategy we had for the previous two cases. Okay. You can't change the pointer from the parent because you've got 2 children out here to worry about. Okay. So the strategy that you adopt is you find the largest pair, or the pair with the largest key in the left subtree, and in this case that would be the 8, and you move it up here to fill this vacancy. Okay. Alternatively, you could find the smallest in the right subtree, in which the case that would be the 15, and you could move it up. Okay. That would preserve the binary search tree property. Okay. All right, so we replace the pair you're removing with the largest in the left subtree or the smallest in the right, and the examples I have consistently replace with the largest in the left subtree. So in this case, an 8. Okay. All right, so this fellow is moved up here. Okay. Now, really what you've done is you've moved the vacant node problem further down the tree. But since you took the largest in the left subtree, what you know is that the node which had this element cannot have a right child, because whatever's in the right child will be bigger, okay, and there's nobody bigger, okay. So this node is guaranteed to not have a right child, and therefore its degree is either 0 or 1. And we know how to handle that from the previous two cases. Okay. In this case, this node's degree is 1, so that means you change the pointer and the parent to the surviving child. Okay. So there's only one pair that has to be relocated. It's not a problem that percolates all the way down the tree. Okay. All right, a last example. You want to take out the 20. Okay. So the strategy is find the largest in the left subtree. The largest in the left subtree is 18. Okay. You find that by moving into the left subtree and then making a sequence of right child moves. Okay. And so the largest item is then moved up. Okay. Largest item has to be in a node whose degree is either 0 or 1. In this case, its degree is 0. In which case, we handle this with the leaf removal strategy. Okay. So you just change the pointer from the parent to null. Okay. Which incidentally is the same as the strategy for the case where a node's degree is 1, because you could say you're changing the pointer from here to that of one of the children, which is null in any case. Okay, so very briefly, that's how you perform puts and removes from binary search trees when you don't care about the height of the resulting tree. Okay. All right, any questions about those? Okay. All right. All right, the complexity of the operation is order of the height. All right, some other operations that you might want to perform on binary search trees. Okay. Operations, say, motivated by operations performed on priority queues. Okay. You may want to find the largest item or the smallest item. Okay. You may want to remove the largest item or the smallest item. So those are standard priority queue operations. Okay. You may be interested in initializing a binary search tree with n pairs. Okay. And the other operation we had for priority queues was meld. Okay. So you may want to do the same thing here. Given two binary search trees, meld them into one. Okay. All right, so let's take a look at how you might perform these operations on binary search trees. Okay. Okay. So if you want to find the max item, we know that you can start at the root and keep making right child moves, keep getting to bigger and bigger items till you can go no further. Okay. So you can find the max item in logarithmic time. In a priority queue, you can find the max item, sorry, not logarithmic, but order of height time. Okay. In a priority queue, you can find the max item in order 1 time. Okay, it's sitting at the root. Okay. So here, it takes you order of height time. You can find the min item. You just follow the leftmost path. You can find the min item. Okay. So that's also order of height. Okay. If you want to remove the item once you found it, okay. Well, once you found it, you can remove it in order 1 time. Okay. Because it's going to be in a node whose degree is 0 or 1. Okay. But if you include the time needed to find the item, then it's order of height. So if you had to implement a remove max or remove min, you could do it in order of height time. It would take you the order of height to do the search to find it, and then order 1, at least with our simple algorithms, to actually take it out. Okay. So the remove time is, if you went into a balanced version of this, this would translate into an order log n time to perform a remove, which asymptotically is the same as that for, say, using binary heaps. If you want to initialize, we know that we can initialize priority queues in linear time. Okay. If you go through and take a look at any one of the many priority queue structures we looked at, binary heaps, leftist heaps, Fibonacci heaps, binomial heaps. In all of them, the initialized time is order of n. Okay. Now, as far as initializing binary search trees is concerned, we can prove there's no way to initialize these in order of n time. Okay. And you prove that by making use of a known result for sorting, which says you cannot sort n elements in less than n log n time. Okay. So you can use a binary search tree to sort. Okay. Given n elements, you first construct the binary search tree. Okay. So that's the initialize step. Having constructed the binary search tree using the initialize operation, you then perform an in-order traversal and list the elements in sorted order. Okay. The in-order traversal takes order of n time. Okay. But we know from theoretical results on sorting that these two steps together have to take n log n time. Okay. So if this step's going to take order n, then this one has to take the n log n. Okay. All right, so you really can't initialize these fellows in anything less than n log n time. If you turn your attention to the meld operation, we know that we can meld two priority queues depending upon the data structure you're using, say in order 1 time, if you had Fibonacci heaps, for example. Okay. Or you can perform the meld in order of log n time if you're using, say, a leftist tree. Okay. Now, it turns out that you can't meld binary search trees in logarithmic time. In fact, you have to spend linear time to do the melding. Okay. And okay. So, for example, if you've got these two binary search trees and you want to meld them into one, so you want to create a new binary search tree, it would look like this. Okay. And to see why you can't do this in in logarithmic time. Okay. We know that the meld operation here is one that can be used to perform a merge on two sorted lists. Okay. And I'll go into the details of that in a moment, but there is a known result for merging that says that if you have two lists, say each having n elements, then there's no way to merge these two lists performing fewer than 2n minus 1 comparisons in the worst case. Okay. So to perform the merge in the worst case, you have to have 2n minus 1 compares. Okay. So coming back to okay, this picture here, okay, right. The way we're going to do a merge, okay. So you're given one list that has n elements, and that's a sorted list. From a sorted list, you can construct the binary search tree with 0 compares. Okay. In fact, you can build a left skewed tree or a right skewed tree. Okay. Just take all the elements with an ascending order, put the first one in the root, the next fellow is its right child, and so on. You get a right skewed binary search tree. Okay. Do the same thing for the second list. Okay. So you can construct the binary search trees with 0 compares if the elements are given to you in ascending order. Okay. All right, so using 0 compares, you construct the two binary search trees. Then you perform the meld. Okay. And then you do an in-order traversal, which also has 0 compares, and you list everything out in merged ascending order. Okay. So there are no compares in creating the initial orange and yellow trees. There are no compares in taking the melded red tree and producing the result in ascending order. You do an in-order traversal. So the only place where compares can be done is in the meld operation. But the theory says to perform this meld, you must do 2n minus 1 compares in the worst case. Okay. So the meld operation has to perform order of n compare operations, and therefore must take at least that much time. Okay. All right, so we can prove that operations like meld and initialize, which were relatively fast for priority queues, cannot be done in a similarly fast fashion for binary search trees. Okay. Any questions about those two claims? No? Okay. All right, so let's turn our attention then to trees whose height is order of log n. Okay. So if you want to perform inserts, searches, and removes in order log n time, we know that they take order of height time, so we have to limit our trees, binary search trees that we use, to a subclass of all the binary search trees, a subclass in which every instance has a height that is order of log n. Okay. And certainly we may look for binary trees that we already know have a height with this property. Okay. So you might say, well, let's limit ourselves to full binary trees. Okay. Now we can see that that's not going to work because full binary trees don't exist for every value of n. Okay. They only exist when the number of elements is 1 short of being a power of 2. And if you want to support a dynamic dictionary, then you have to be able to go from 7 elements to 8 to 9 to 10 to 11 and 12. You can't just say, now at 7 I won't do anything till you give me 8 more elements. Okay. All right, so full binary trees aren't going to work. We could look at complete binary trees. We know that these exist for all values of n. Okay. And we know that their height is logarithmic, but we can show that if you stay with complete binary trees, then you cannot perform insert and delete in logarithmic time. Okay. To see a simple example, okay, so here's a complete binary tree. It's a binary search tree. It has 5 elements in it. Okay. And we're going to perform an insert in this, and I'm going to insert an item that is smaller than the smallest you presently have. Okay. So maybe anything smaller than 2. Okay. So once you're done, you started with a 5-element complete binary tree, you have to end up with a 6-element complete binary tree, so its structure is well defined. Also, the placement of elements has to be such that if you perform an in-order traversal in there, you get them out in ascending order. So the placement of elements is also unique. Okay, the structure is unique and the placement is unique, and like it or not, this is what you have to produce. Okay, and what you see is that to go from here to there, you have to relocate almost every element. Okay. All elements change their position in the tree. If you even think of keeping this as a linked binary tree, you'll see that for every element there, its parent has changed, or both of its children, or one of its children have changed. So for every node, you're going to have to make some change. And that's going to take you order of n time. Okay. All right, so complete binary trees are not suited either for dynamic dictionaries. Okay, okay, so that kind of eliminates the tree types that we know of already that have a log n height property. Now, as far as balanced search trees are concerned, balanced search trees, very loosely speaking, would be anything, any class of trees whose height is logarithmic in the number of elements. Okay. There are many different categories of balanced search trees, or balanced trees in general. Okay. We would have a category which we would call height balanced trees. Okay. And in that category there's a specific variety called the AVL tree. The Edelson, Velsky, and Landis, these are the 2 Russians who came up with this class of trees. And this really represents the first known class of log n height trees for which people could perform inserts and deletes in logarithmic time. So historically, it's of great significance. It's the first example of a dynamic dictionary structure where you could perform things in logarithmic time. Okay. All right, we will be studying these. Okay. Then there are weight-balanced trees, of which there are a few varieties, but we're not going to be studying any variety of weight-balanced tree in the class. Okay. Then there are degree-balanced trees, and in this category there's a variety called 2-3 trees that we'll be looking at. A generalization of them, 2-3-4, which we'll also look at. It's a category called red-black trees, which is really, they're really the same as 2-3-4. It's just a different way of representing a 2-3-4 tree than the natural way to represent a 2-3-4 tree. Okay. There are B trees, and really when you look at B trees, all of these other three things are just special cases of a B tree. Okay. So in some sense here, there's only one different type of tree. We're looking at B trees, and these two are direct special cases, and this one is just another way to represent 2-3-4, which is also a special case of a B tree. Okay. All right, so we're going to look at quite a few search tree varieties. Okay. And depending upon the application, one or the other may prove to be the better way to go. Well, let's start by looking at the first of these, the AVL tree. Okay. All right, it's a binary tree, and as I said a little while ago, it's a height-balanced binary tree, and to understand what we mean by height balancing, we'll define a quantity called the balance factor for every node in the binary tree. Where the balance factor is simply the difference in heights between the left and the right subtrees. Okay. Now, we're going to define the balance factor as being height of left minus height of right. In some books, you might find it defined the other way around, height of right minus height of left. It doesn't really make any difference. Okay. It just means that you change the sign of the balance factor. Okay. All right, the requirement, okay, regardless of how you define it, height of left minus right or right minus left, the requirement is the same. To be an AVL tree, the balance factor of every node should be -1, 0, or +1. Okay. So yeah.
So basically, the two children of a node can only differ by at most one level.
That's right. So what was said is that basically the height difference between the left and right subtrees is at most 1 for every single node. Okay. Right, as an example, consider this binary tree here. We can fill in the balance factors. Okay. The balance factor of a leaf is 0. Height of left subtree is 0. Height of right subtree is 0. Height difference is 0. Okay. So the balance factor there is 0. Okay. If you come here, height of the left subtree is 1. Height of the right subtree is 1, so the height difference is 0. If you come to this node, the balance factor is 0. Okay. Moving along here, the height of the left subtree is 2, right subtree is 1, so the balance factor is +1. Okay. So 0 out there. Over here it's going to be -1. Over here it'll be a 0. Over there it'll be a +1. Okay. And then here it's a 0, -1. And over here it's going to be a +1. The height here is 3, and the height here is 2. Coming over here, the height of the left subtree, there are 3 levels, 1, 2, 3, and down here it's 1, 2, 3, 4. So 3 minus 4 is a -1. Okay. All right, so in this particular example, the balance factor of every node is one of the permissible values, -1, 0, and +1, and therefore this is an AVL tree. It's not difficult to convert it into something that will not be an AVL tree. Just throw a node down here. Okay. So if you give this fellow here a right child, then the balance factor of this node would become -1, and the balance factor there would become -2. Okay, so a height balanced binary tree, the essential property is that you place a bound on the height difference between the left and the right subtrees of every single node. In an AVL tree, that bound is 1. Okay. The absolute value of the height difference cannot be any more than 1. But you could go to other height balanced trees and say the absolute difference in the height is no more than 2 or no more than 3. Okay. And it doesn't really matter what bound you place. You can prove that the class of trees you define has logarithmic height. Okay. It's just that the base of the logarithm would change. Okay. Now we're going to go through a proof that shows that when the height difference bound is 1, namely when you have AVL trees, that the height of these trees cannot exceed something like 1.44 log of n. Okay. And since we know that every n-node binary tree must have a height that's at least log of n, okay, we know that the height of AVL trees lies between the lower bound for every single binary tree and the upper bound for AVL trees. Okay. So your height could be anywhere in this range. And then if you're able to perform your inserts and deletes in order of height time, okay, we're going to have to modify how we do inserts and deletes, because if you stick with the simple algorithms, even though you may start with an AVL tree, you do an insert, the result may not be an AVL tree. You might move out of the class. Okay. So you have to preserve the class property. Okay. All right, so let's come up with an upper bound on the height, okay, the 1.44 log n. The analysis is really very similar to the analysis done for, say, binomial heaps, showing that if the degree is something, then you got to have 2 to the degree, or for Fibonacci heaps, which said that if the degree was I, then you've got to have phi raised to I or phi raised to I plus 2 number of nodes. So here too, we're going to say, well, suppose you have a particular height. Okay. Well, then what is the minimum number of nodes the AVL tree could possibly have, given that height? And that minimum number of nodes needs to be some exponential function of the height. Okay. Okay. All right. So as in the case of the Fibonacci heap analysis, we will say let n sub h be the minimum number of nodes in an AVL tree whose height is h. There, of course, we were looking at a Fibonacci heap whose degree was h. Okay. So instead of degree, we're now talking about height. Okay. All right, if the height of your tree is 0, well, then you have no nodes. Okay. So n sub 0 is 0. If the height is 1, then all you have is the root. So n sub 1 is 1. Okay. If the height is more than 1, okay, then we draw a little picture. You got to have a root, okay, and then the root has a left subtree and the root has a right subtree. Okay. We know from the definition of AVL trees that the left subtree must be an AVL tree and the right subtree must also be an AVL tree. Okay. Now, if this tree shown here is one that has the minimum number of nodes possible in an AVL tree of height h, then we can reason that L, okay, well, I guess before I do that part, let me take care of this statement here. Okay. The height of the whole tree is h. Okay. So we know that the height of the left subtree is at most h minus 1. Okay. And the height of the right subtree is at most h minus 1. And one of the two has to be h minus 1. Okay. If both were h minus 2, for example, the whole thing can't be h. Okay. So one of the two has a height that's h minus 1. Okay. The other one could have a height that's h minus 1 or h minus 2. Okay. Now, we can reason that the value of n sub h increases as you increase h. Minimum number of nodes in a tree whose height is 0 is less than that in a tree whose height is 1, and then if you go to height 2, the minimum number will go up, and so on. Okay. So if this whole thing here has the minimum number of nodes in an AVL tree whose height is h, if this fellow is h minus 1, then that guy will not be h minus 1, because we can reduce the number of nodes by changing this to have a height of h minus 2. Okay. So one tree has a height that is h minus 1, the other one has h minus 2. It doesn't really matter which one is h minus 1 and which one is h minus 2. Okay. So if the whole thing has a minimum number of nodes, okay, then the fellow whose height is h minus 1 will have this many nodes in it. If it has more than that, we can throw out the L and put in an AVL tree here with smaller number of nodes. Okay. So since the whole thing is minimal, L and R are both minimal for their heights, so one of them has nh minus 1, the other one has nh minus 2. Okay. And that gives us a familiar recurrence. Okay. It says the minimum number of nodes when the height is h is the minimum number of nodes when the height is h minus 1 plus the minimum when it's h minus 2. So one takes care of L, the other one takes care of R, and then this one here takes care of the root. Okay. Well, that looks a lot like the equation we had for Fibonacci heaps. Okay, we've seen the Fibonacci numbers before, given by those two recurrences. Here's what we have for the minimum number of nodes in an AVL tree. From these two recurrences, we can derive this recurrence. You can prove this using induction. And then, knowing how fast the Fibonacci numbers grow, okay, we know that the ith Fibonacci number is roughly phi raised to I divided by root of 5, where phi is 1 plus root 5 over 2. Okay. So using this stuff, okay, all right, so from here, basically what you get is the minimum number of nodes in an AVL tree whose height is h is phi raised to h plus 2 over root 5. Okay. So the minimum number of nodes is growing exponentially, and if you then turn around and bring the n to one side and the height to the other side, okay, you can come up with the equation we had before. That the height is no more than 1.44 log of n. Okay. All right. So that's really that's almost identical to what we went through for Fibonacci heaps. Okay. All right. An AVL search tree is simply an AVL tree with the binary search tree property added to it. So you don't have to use AVL trees only in the context of search trees, but when you do use them in the context of search trees, so they're binary search trees with the property that the height difference between left and right subtrees is at most 1. Okay. And most of the time, oops. Okay. All right, so most of the time we won't use the full name AVL search tree. We'll just call these AVL trees, because we're only going to use them in the context of binary search trees in this class. Okay. Now, as far as searching these is concerned, okay, there's no difference between searching an AVL tree and searching any other binary search tree. The same algorithm works. You don't have to make any change. We don't care about the balance factors. Okay. The difference is going to come in how you insert and how you remove. Okay. We'll take a look at those operations in our next meeting. Okay. Okay.
belt.
All right, we were looking at AVL trees as our first example of a balanced tree last time. This was a height balanced tree. Today we want to basically look at how you would perform inserts and removes from an AVL tree while preserving the AVL property. Okay. All right, so first a quick review of AVL trees. We saw that an AVL tree is a binary tree, and you define a balance factor for every node, where the balance factor is simply the height difference between the left and right subtrees of that node. AVL trees have the property that the balance factor of every node is -1, 0, or 1. Okay. And as a consequence of this property, we saw that the height of an AVL tree lies between log n and 1.44 log n. So they have the right height property. All AVL trees have a height that is order of log n. Right, as an example of an AVL tree, this is really an AVL search tree. The elements are placed to satisfy the binary search tree property. The structure of the underlying binary tree corresponds to that of an AVL tree. The numbers given outside are the balance factors. So all of the balance factors have one of the allowable three values, +1, -1, and 0. And inside we've got the keys of the elements satisfying the binary search tree property. Okay. All right, so with that as a recap of what we did last time, let's take a look at how to perform first the insert operation. Okay. All right, so suppose you want to put into your collection a pair whose key value is 9. Okay, so we want to insert a 9. Okay. We'll proceed to perform the insertion exactly the way we would if we didn't care about balance. Okay, so let's just use the algorithm we were using when we talked about binary search trees a couple of lectures ago. And that algorithm, if you recall, would search for the 9. So it's smaller than 10, you end up here. Bigger than 7, you end up there. Bigger than 8, you fall off here. And where you fall off is where you put it in. Okay, so you get a new node, you put in a key value, and then you make the connection. Okay. Now we need to adjust the balance factors on nodes in the tree so that the balance factors are recorded correctly. We know that the only balance factors we need to be concerned about are those on the path from the root to this newly inserted pink node. Okay. It's only along this path that the height of subtrees could change. Down here you didn't do anything, so none of those subtrees could have a height change. Same thing around here, you didn't do anything, so none of those subtrees have a height change. Okay. So we move downwards, we make the insert, okay, and then we're going to retrace the path backwards, adjusting the balance factors. Okay. We would typically not adjust the balance factors on the way down because the insert might fail in the sense that you might already have a pair whose key is 9, in which case you won't insert a node, you might update the associated element. Okay. All right, so having made sure that I'm really going to add a new node, I will now set balance factors on the way back. Okay. The balance factor of the new node, of course, is 0. Okay. That's always 0. It doesn't come with a left or right subtree. Okay. When you move backwards from a right subtree, okay, the balance factor of this node will decrease by 1. Okay. It's height of left minus height of right. So since the height of the right subtree went up, it was previously 0, it's now 1, the balance factor here will decrease by 1, so this becomes -1. Okay. The height of this subtree was previously 1, it has now become 2. Okay. So the same thing, you're coming from the right subtree, so the balance factor there is going to decrease by 1. Okay. So that balance factor becomes 0. Okay. When a balance factor becomes 0, we know that the height of the subtree rooted at this node has not changed. Okay. It was previously 1. The right subtree increased its height by 1. The balance factor has become 0. The overall height of the subtree is unchanged. Okay. So when you reach a node whose balance factor becomes 0, then you don't need to go any further up because none of those balance factors will change. Okay. All right, so to change balance factors, you start from the new node and you move back up. Okay. And some nodes that had a balance factor of 0, their balance factor would change to +1 or -1 because the height of a subtree changed. Okay. When you encounter the first fellow whose balance factor was +1 or -1 before the insert, its balance factor would now change to 0. Okay. Or of course it would become +2 or -2. Okay. It's going to change by 1. Okay. So if it was a +1, it could go to a 2, it could go to a 0. If it was -1, it could go to a 0, it would go to a -2. Okay. If it goes to 0, the height hasn't changed, so you don't need to go any further up. Okay. Let's try another one. Okay. Let's try and insert a 29. Okay. All right, so the process is the same. You start at the root, follow the search path. Okay. Bigger than 10, smaller than 40, smaller than 30, bigger than 20, bigger than 25, you fall off here. Right. So wherever you fall off, that's where you put in a new node. Okay, so you get the node, you put in the key, and then you make the connection. Okay. Having done the insert, we're now going to set the balance factors, starting from the new node, going back up the tree. Okay. The balance factor of the new node is always 0. And the new node always causes the height of that subtree to increase by 1. Okay. So long as the height changes, you have to go further up the tree. Once the height doesn't change, you can stop. Okay. All right, so the height of this subtree has changed, has gone up by 1. You're coming from the right subtree, so you have to decrease the balance factor by 1. If you were coming from the left subtree, you would increase the balance factor by 1. Okay. All right, so the balance factor becomes -1. When the balance factor changes from 0 to something, the height has increased. Okay. So you have to keep going up. Okay. All right, so from this node, I now move up to that node. I'm coming from the right subtree, so the balance factor decreases by 1. It becomes -2. Okay. All right, so my backward pass up here is going to stop, at least initially, at the first place where the balance factor becomes +2 or -2, signaling I have a problem. Okay. I'm not going to continue to fix balance factors. I'm going to immediately move into a recovery or readjustment mode for the tree. Okay. All right, so this backward pass where you readjust balance factors stops at the first node where the balance factor becomes +2 or -2 if there is such a node. Okay. Otherwise, it will keep going until you reach a node whose balance factor becomes 0. At that time you can stop, or you find your way all the way out of the tree. Okay. All right, so in this example, we reached a node whose balance factor became -2. Okay. And at that time, we'll say we have an imbalance. Okay. The imbalance that we have is characterized based upon the location of the new node, the pink node, relative to the white node, the node whose balance factors become +2 or -2. Okay. In this particular case, this pink node was first inserted into the right subtree of the white node. Okay. So that'll give me the first letter in the characterization of the imbalance. Okay. Right. So you identify the white node, also called the A node, is the nearest ancestor of the newly inserted node whose balance factors become +2 or -2. Okay. If the pink node was inserted into the right subtree of the white node, then it's an imbalance of type R. That gives you the first letter in the characterization. The second letter comes relative to the root of the subtree you went into. Okay, so from here I went into the right subtree, and then from here I further went into its right subtree, so that gives me the second R. If this pink node was sitting down here, this would be called an RL type of imbalance. Okay. All right, so we characterize the imbalance based on the A node, the nearest ancestor of the newly inserted node whose balance factors become plus or minus 2. We use a two-letter characterization. In this case, it's an RR imbalance. Okay. We know that the A node, okay, will always have, okay, if you would have had a, well, let me put it differently. We know that the pink node cannot be a child of the A node. Okay. It's got to be a grandchild or further down. Okay. If there was a possibility that the pink node could be a child, then you wouldn't be able to come up with the second letter in the characterization. Okay. It can't be a child because the balance factor here had to be a +1 or -1 before the insert. Okay. And therefore this node had to have a subtree, and it must have had a non-empty subtree on the side where you did the insert. Okay. All right, so you can convince yourself that whenever you get a +2 or -2, this characterization is well defined. The first node is easy to see, and then you need to convince yourself that it will actually have a child that was there from before, whose subtree you moved into. All right, so that kind of imbalance said is called an RR imbalance, and the way you fix an RR imbalance is you perform what's called an RR rotation. In an RR rotation, you simply rotate the subtree rooted here, okay, counterclockwise. Okay, so this node, the right child of the A node, takes the position of the A node. The A node becomes the left child of this guy. Okay, there's some other changes which we'll see in the more general picture that we're going to look at in a moment. Okay, so in this case you perform an RR rotation, and in this particular example, once you do the RR rotation, you find that the height of the subtree rooted here is the same as it was before the insert. Okay, so there's no need to go any further up the tree. Okay, so if you compare with the previous picture, okay, so before you did the insert, the height of the subtree rooted at this position was 2. You had the white node and that orange node or gold node. Okay. After you do the rotation, at that same position, the height is still 2. Okay. The balance factor becomes 0, and there's no need to go further up the tree. Okay. So in this particular case, the rotation fixes the problem. Okay. All right, so as far as inserts are concerned, okay, the general strategy is you first insert the item as though you would perform an insert in an unbalanced tree. Okay. Then you have a backward pass from that newly inserted node in which you change or you adjust balance factors to their correct current value. Okay. This backward pass will stop when you either reach a node whose balance factor becomes 0. That represents a subtree whose height doesn't change, and so you don't need to go any further up. Or it would stop when you reach an A node, okay, a node whose balance factor becomes 2 or -2. Okay. Or it would stop when you really fall off the tree, so you're backing up from the root. Okay. All right, so if you reach a node whose balance factor becomes 2 or -2, then you have a problem, and that's when you need to do something special. Otherwise, if you stop at a 0, or once you've trying to back out from the root, you're done. You don't have to perform any corrective measures on your tree. Okay. All right, so if you do have a node whose balance factor becomes +2 or -2, we'll say the tree is unbalanced. Okay. We define the notion of an A node. It's the white node that we had in that example. nearest ancestor of newly inserted node whose balance factor becomes +2 or -2. Okay. All right. Something to note or observe is that if you look at the nodes between the A node and the newly inserted node, the pink node, okay, then prior to the insertion, all of those nodes must have had a balance factor that is 0. Okay. To see that, suppose somebody on that path had a balance factor that was 1. Then on your way back, if you had a 1, you'd either change the 1 to a 2 or a 0. If you changed it to a 2, well, that node would have become the A node, so you wouldn't have gone further up. If you changed it to a 0, you'd have stopped. Okay. So between the A node and that new pink node, everybody must have had a balance factor 0 before the insert. Okay. All right, any questions about that observation? You want to see a picture, or you okay? Yeah? Everybody okay? All right. Okay, so let's take a look at the different types of imbalance and how you fix the problem resulting from that imbalance. Okay. We saw an example of an RR. RR simply means that your new node, that pink node, is in the right subtree of the right subtree of A. Okay. And then you can have an LL, it's kind of symmetric to the RR. You can have an RL. Okay. So you went into the right subtree of A. The first letter tells you whether you're going to the left or right subtree of A. So you went into the right subtree of A, and after that, you went into the left subtree. Okay. And then the fourth type is the LR. Okay. All right, so LL and RR are symmetric.